So first, I'd like to thank Marius also for the initiative and implementation to organize this conference. It's a great privilege to be part of this conference. And also, it's a great privilege and a great fortune for me to have been a student of Vila in the 90s. And I'd like to thank him for his incredible support over many years. I'm going to talk about a very specific problem in general relativity, but it's the kind of problem that almost everything becomes harmonic analysis, becomes what's called bilinear estimates. Bilinear estimates is what it says, so it's just the estimates on products of functions, essentially, or certain types of products of functions. And it's a problem that I'm going to start with some slightly simpler version of these bilinear estimates just to understand what they are. They go back to so the idea of using bilinear estimates, it goes back to the early 90s, and its work originally of Bourgain and Koenig-Ponce and Vega. And there are several equations one could look at. They're all semi-linear equations. For example, the simplest equation of this type is the KdV equation. And the KdV equation is written here. We are looking at an evolution. So it's an evolution in which we start with data at time t is equal to 0, and we evolve the function u according to partial differential equation. The partial differential equation is a very simple model here. The KdV is dt plus I lambda u. It's u times dxu. And lambda in this case it turns out to be dx cubed, which in the Fourier space is written as c cubed. I write it this way just because later on we are going to see things in this way. And one would like to understand this equation. To understand the solution of this equation, one can write it in terms of the Duhamel formula, and it becomes u of t is a linear part e to the minus it lambda phi plus a nonlinear contribution. This is the Duhamel formula. The second term is the nonlinear contribution, and which reads e to the minus I t minus s lambda times the nonlinearity. And the solution u should be thought of as a solution, can be thought of as a solution of this equation in integral form. And then the theorem of Bourgain is local positiveness in L2. And local positiveness in L2 means that we like to understand this equation as a fixed point of the solution u should be a fixed point of an operator on L2. And the space in which one runs the fixed point argument is this very famous space by now, the so-called XSB spaces. Which are obtained in the following way. One looks at the Fourier transform of f, and one multiplies by 1 plus xi squared to the power s over 2. This has to do with the Sobolev space in which one works. And then one multiplies with something that restricts to, something has to do with the equation. So in this case, it's tau minus lambda of c to a certain power b. And the key step, so the whole proof of Bourgain is this bilinear estimate, which is written at the bottom of the slide. So it's the bilinear estimate here. That says that if we look at the product of two functions f and g, and if we measure them in this space xs, in this case s is equal to 0, so x0 b minus 1, and that's controlled by the product of the two functions in the space xsb. So this is what I mean by a bilinear estimate. One can see two things. So bilinear, first of all, it's just on a product of two functions. What's very important in all of these theories is to work on spaces that are dictated by the equation. So one doesn't do bilinear estimates in spaces. We don't get to choose which space to do it. It has to be done on space that are dictated by the equation. So this kind of proof. This started in the early 90s. Now, there was lots of work. In fact, there was earlier work of Klein-Macedon on semi-linear wave equations. Pretty much many semi-linear equations, once these ideas became available, these ideas can be extended to many semi-linear equations. It turns out that one basically has to replace the lambda and run the fixed point argument in the appropriate space. These are almost optimal, this space is XSB. It turns out they're almost optimal except for endpoints that correspond to small data critical problems. And this is small data. In order to run the fixed point argument, one can think of this as small data, but because of conservation laws and rescaling, this becomes a general large data global regularity problem. Okay, so this is the kind of estimates that come in to this problem. One can also see them One can also see more explicitly what operators we are looking at if we write out explicitly the Duhamel formula. And up to the quadratic part, it's very easy to write it out. So in this problem, if we are looking at expanding the solution, so if we think that the data is small and we expand the power of the solution, then we get these expressions. So the first line is the linear contribution, and the second line is the quadratic contribution. So if we plug in, as if we run the fixed point argument and we plug in the first approximation and we plug in into the formula and we get the quadratic approximation, the quadratic contribution. And the quadratic contribution, if we look at it, what it says, it's so it reads e to the minus it lambda of psi, and then we have a convolution of the data with itself, so phi of xi minus eta times phi of eta. Then we have this more complicated fraction, and the more complicated fraction reads 1 minus e to the it times this phase, lambda of xi minus lambda of eta minus lambda of xi minus eta, divided by that same phase. So if we are to think that we can analyze the whole solution, at the very least, of course, one has to understand the quadratic portion of the solution, the quadratic part. And the quadratic part is exactly this integral. It looks like, it's kind of like, one can see how it looks. It looks like a convolution, but then there is this particular resonance function. So this is called the resonance function lambda of xi minus lambda of eta minus lambda of xi minus eta. And that comes in two places. It comes as a denominator, so one has to understand how big the zero set of that function is. And it also comes as a numerator. When that phase is exactly zero, of course, the numerator cancels the denominator, but then as the time gets very large, the contribution of the thin sets becomes more and more important. So it's the bilinear estimates means that one has to understand this type of convolution operators. These are just the quadratic parts. Afterwards, it gets harder. So the cubic part would be more complicated. So one has to do it in a way that's that one can move forward. But already, just from this formula, and we see what is the key, what is the first key component of the proof is to understand the size and the shape of the sublevel sets of these faces, and the faces are obtained by taking the superpositions of these functions lambda. And it turns out that in some problems, the signs of lambda can be plus minus. That's because sometimes the function u bar will come in. In many problems, the function u bar will also come in the nonlinearity, and that will contribute the opposite sign. Okay, so this is all very classical. It's been a lot of work over the last since the early 90s, so 25 years now, doing this type of analysis for many equations. There's one critical issue. There's one issue with all of this, which is that in most problems, many problems in mathematical physics and many natural evolutions, they are quasi-linear problems. They are not semi-linear. And what this means in a quasi-linear problem, quasi-linear means that there is a loss of derivative somewhere. So in a problem that's quasi-linear, like for example, all like for instance, the Euler equations, the Einstein vacuum equations, so most equations of mathematical physics, they are quasi-linear problems, which means that there is no space. In a quasi-linear problem, the issue is that there is no space in which one can write this fixed point argument. It's not about fixing the space, but there's somehow a loss of derivative in the nonlinearity that will not allow this fixed point argument to be run in any space. On the other hand, quasi-linear is just one step removed from semi-linear. So the only loss happens because of a loss of a derivative. It's not like a fully nonlinear problem which we don't know what to start from. It's a quasi-linear problem. So the only loss happens because of this loss of derivatives. And in these problems, there's been a lot of activity also in the quasi-linear problems. And going back at least to the 80s. Now the local theory, to understand the local theory, in all of the problems I'm going to talk about, the local theory is not an issue. So to construct the solution on a short time interval, starting from data at time 0 to construct the solution on a short time interval, there's not an issue. That can be done using energy estimates. And in all of the problems that I'm going to talk about, there's the situation. Now, if one wants to go beyond the local regularity, there are two basic possibilities. Either one has some kind of blow up in finite time, or one has global solutions that extend for all time. Now, I'm going to talk about the issue of global regularity. And here, there's been some very classical work in the 80s, starting with John and Kleinerman, and this method. So there's the vector fields method of Kleinerman and Christodoulou. And this is very classical work that depends on what's called the method of vector fields. And this method of vector fields being very suitable and very strong in situations where there are lots of symmetries of the problem. And it led to, like, for example, it led to the theorem of Christodoulou and Kleinerman on the global regularity of the global stability of the Minkowski spacetime for the Einstein vacuum equations. Now, the method of vector fields is very strong. However, one has to have enough many vector fields in order so one has to have enough many symmetries in the problem. And it becomes a lot less effective if you're looking at more complicated systems. And this is the kind of situation I want to talk about. There are these so-called two-speed problems. So if you have more complicated systems, imagine you have some sort of coupled system of wave equations and Schrödinger equations, or wave equations, and wave equations at different speeds. These are natural when you think of plasma models. Then in principle, you have vector fields for each equation at a time, but they're all coupled, and there are no joint vector fields for all of them at the same time. And because of this, this vector fields method, they become a lot less they are not. It's harder to implement them if one has problems in which you have coupled systems which don't have enough many joint vector fields. So the models that are of this type are the plasma models and the water wave models. And my talk is going to be about two ideas that are new in the context of quasi-linear problems, but they are very classical in the context of semi-linear problems. So the new ideas that came in are both originate from semi-linear problems. One of them is to use normal forms. So the normal forms of that have been used a lot in semi-linear problems going back to the 80s, the normal forms of Chatat, which are basically integration by parts arguments in time. So one integrates by parts in time, and the goal of integration by parts in time is to say that the quadratic nonlinearities can be reframed as cubic nonlinearities at the expense of other terms. And a second idea that's also very common in semi-linear equation is the use of the designer norms. So all of these arguments, they depend on having good norms in which one can run, in which one can prove the fixed point argument. So for example, Bourgain's XSB norm, that's one example of such a norm. Schematically, so to explain schematic, I'm going to talk about a very specific problem, but I just want to give a general scheme of how we could try to run things. So let's say we're looking at a quasi-linear evolution of the form Lu is equal to n. So I'm going to think that L is the linear part and n is the nonlinearity. And then we are going to control the solution using two norms. We are going to use, on one hand, energy norms, and on the other hand, these designer norms. And we assume, we run everything through a bootstrap argument. So we assume that we have control on some time interval of both the energy norms and the z norm by a constant, and the time 0 we assume that we have control by a smaller constant. Then what we want to do is to improve the control on the time interval of the evolution, and we do it in two ways. So for the energy norms, for the energy norms Hn, we use energy estimates, and for the z norm, so the designer norm, we use the Duhamel formula. And the way to think about this is that the norm, so the energy estimates are at a high order of derivatives, but they are somewhat, they are kind of rough. So they measure derivatives, but they don't measure decay. So for example, they by themselves would work also in periodic cases. So they don't measure decay, but it's the z norms that they measure decay, among other things. They measure dispersion and decay. And but they are at the lower order of derivatives. The point being that we don't need to have control of these decaying norms at the highest order of derivatives. Now, the way I think about the Z norm is basically one has to look at the Duhamel formula. One has to identify what are the stationary points when we write the Duhamel formula as an oscillation, and usually they come. So to identify a good norm, one has to look at the stationary points, and these are called space-time resonances, and that's how one identifies a good norm, a good Z norm. So this is the bootstrap argument that we want to plan. Now, if we just look at it, the energy norms, I just wrote it as a Sobolev norm, but in principle you should think that it's the Sobolev plus all the vector fields that you have in the problem. Because the Sobolev norm is just as if you apply the vector field d by dx1, but in principle one can apply all the vector fields that commute with the linear part, and in principle the difference is not too big. Now, if we look at this, this is a bootstrap argument, and bootstrap is like an induction. What's very important to be able to run is to have a good Z norm, and good relative to this type of argument. You see what happens if we make the Z norm too strong, then we will know more, but we have to prove more, and at some point it might become false. If we make the Z norm too weak, then we might not know enough. So it's important to have a good choice of a norm. And it will depend, of course, on the equation as well. And so this kind of argument, we've done this over the last few years. So I've done this over the last few years with several collaborators, and the names of the collaborators are at the bottom of the slide. They are Benoit Pausader, Ying Guo, Fabio Pusateri, Yu Deng, Javier Gomez Serrano, and Diego Cordoba. So we've done several projects on quasi-linear problems, the issue being to construct global solutions in these projects. I'm going to talk about the third project, the Einstein-Klein-Gordon system in General Relativity, but just to put them in a context. So we've worked on plasma models, which are determined by the Euler-Maxwell equations. In the plasma models, this is two-speed problem. This is the simplest two-speed problem, which one has two types of particles, ions and electrons. Some of them move at the speed of light, some of them move at the speed of sound, according to essentially wave equations. And we have to construct global solutions, and we've been able to do it using this kind of mechanism that I described. In the case of irrotational and in the Euclidean geometry. Then we've done work on water waves. So water waves, these are free boundary Euler equations in which one has a fluid that moves according to Euler equations, and the boundary also moves. And again, there we are looking at small and localized data in the irrotational case in the Euclidean geometry. Then the problem that I'm going to talk about is a problem in general relativity. It's called the Einstein-Klein-Gordon system. And it has a better structure, but I wrote it here just the final result. So the Einstein-Klein-Gordon system says that the Ricci tensor of the metric. So in the Einstein-Klein-Gordon system, one has a metric and a field, so a scalar field psi and the metric G. And then from the metric, one produces the Ricci tensor. So it's the Riemann and then the Ricci. And the equations, these are the equations for the Ricci tensor. And they read the Ricci tensor of the metric is a certain product, d alpha psi d beta psi minus psi squared g alpha beta. And the psi itself, it satisfies a wave, or in this case a Klein-Gordon equation of the form box psi is equal to psi. So this is the point I'm going to talk about. The case psi is equal to 0, it's the classical theorem of Christodoulou and Kleinemann, because that just becomes the Einstein vacuum equations. And we've also done work on the generalized SQG patch equation. So there the issue is again to produce global solutions in a neighborhood of a fixed stationary solution. Now, I'm going to talk more about this Einstein-Klein-Gordon system, but just to get a sense for what it says, because these are geometric equations, and the issue is how much is the Ricci tensor. So how does this system close? So just to have something easy to think about, I'm going to. It's a reasonably good model, and it's very helpful to have this kind of models because we see the problem. This doesn't quite cover the whole problem, but it's a much more elementary model. So the model that we are looking at is the so-called wave-Klein-Gordon model, and we are looking at a system of two things: wave equation box U is equal to a nonlinearity, and Klein-Gordon equation minus box plus 1v is equal to a nonlinearity. And the nonlinearities are of the following type. So the one for the Klein-Gordon is a quasi-linear nonlinearity of the form u times d2v. And the one for the wave equation, we simplify it a lot, but we still put a semi-linear term of the form gradient of v squared. So this is a very simple model that still says something about the full Einstein-Klein-Gordon system. If you think, so the V, if you compare, the V would correspond to psi, so that's a simple correspondence. Now the U, this corresponds to the metric, and the Einstein equations, they have to do the wave equations for the metric. And in this case, we have, so this is the model that we are looking at. If we think, this is essentially a two-speed model, because if we think the wave equation, it propagates at speed 1, it's the speed of propagation for the wave equation, it goes along the cone, so it's speed 1. While for the Klein-Gordon equation, the speed is always strictly smaller than 1. So at a fixed frequency, the speed could be 1/2. So it's the whole range of frequency is strictly smaller than 1. So there are propagations of different speeds in this problem. Now, so this is a problem to model the full system on. Now I'm going to go and talk about the full system, and first I'm going to describe. So I want to say several things. So first I'd like to say how is it that this Einstein-Klein-Gordon system can be seen as a PDE problem, because the way it's written now, we don't know how much the Ricci tensor is, so we have to understand that. And then I'd like to say, I will state the theorem that we have, and then I will look at the model system and explain the main difficulties that come in, but only in the model system because they're easy to see and they're very easy to isolate. So that's going to be that's the plan for the rest of the talk. So we are looking, as I said, this is a geometric problem. So you're looking at the metric. It's a 4-dimensional. Everything is 4 dimensions. So you're looking at a 4-dimensional metric G and the field psi. Now, it turns out it's Lorentzian. Lorentzian means that it has the signature of the Minkowski metric. So it's 1 minus and 3 pluses. For the purpose of calculating, just for the formulas, it makes no difference that it's to be a Riemannian. And so this is just a general, so one induces a covariant derivative. So the main question that we are going to prove is the global stability of the simplest solutions of the Minkowski metric in the Einstein-Klein-Gordon system. And here I have some elements of the geometry just to go through how one derives PDE equation starting from the geometric equation. This is very classical. So one looks at the metric, one has a covariant derivative, one defines the gamma coefficients according to, by taking derivatives of the metric. There's a formula for the covariant derivative. Now we are going to work in the harmonic gauge. So these gamma coefficients, which are traces of the connection coefficients, in the harmonic gauge, they are set to be equal to 0. So you're going to use, in some sense, you're going to use this idea of working of solving the Einstein vacuum equations in the harmonic gauge, which goes back to the work of Lindblad and Rodniansky. And then once we understand, so this is the picture. So we have G. Let me write them without the formulas, but from the metric. So the metric produces the covariant derivative. The covariant derivative produces the Riemann tensor, and the Riemann tensor, by taking the trace, one gets the Ricci tensor. So this is the Ricci tensor, and this is the one that comes in at the end in the equation. And one gets the following formula. So for the Ricci tensor, one gets some kind of box of every component of the metric and then plus more terms, more nonlinear terms in the, it's this reduced box that, that we are using, so box tilde G being G alpha beta D alpha D beta. And then there are more terms in the, more semi-linear terms in the, in the formula for the Ricci tensor. And one has, these are the explicit formulas, so the Ricci tensor contains also these terms f, which are of the form of, they're all quadratic, all of these terms here are quadratic, and they are quadratic expressions containing various derivatives of the metric and various, and the gamma coefficients. And I divide them into, so I divide the quadratic terms into two types, the Q terms, which are the good terms, and the P terms, which are the bad terms. The good terms, they have a certain null structure, while the bad terms, they don't have that null structure, but they are much fewer, as we can see. Okay, so this is basically a formula. The main thing to get from here is that there is the formula that expresses the Ricci tensor in terms of the metric. One has to look at the two derivatives of the metric, and then lots of terms that have to do with one derivative of the metric. And this is formalized in this calculation that if we are looking to solve the Einstein-Klein-Gordon system, and we are looking to work in the harmonic gauge in which the gamma coefficients are equal to 0, then that's equivalent to the system of wave equations for the metric components G. So these are box G alpha beta plus gradient of psi squared plus these nonlinearities for the metric, for these more complicated terms that are quadratic terms in the metric is equal to 0. And then we have the Klein-Gordon equation for psi. And this is basically equivalent, so solving this system in this PDE form, so solving the system that's written over there, one can go back and forth, and once we have a solution for the system, we can create a solution for the Einstein-Klein-Gordon system. And the condition, so the harmonic gauge condition is preserved. So now I'm going to state the theorem. This is our main theorem. It's a joint work with Benoit Pausader. And so the theorem says the following, that if we are looking at an initial situation, initial state that is close to the solution, the Minkowski metric with the Minkowski metric comma 0, so this means that we are looking at a metric that's prescribed on initial surface. The norms, I didn't write exactly the norms because they're a little more complicated to write, but one should think that they are natural norms relative that are consistent with the kind of solutions one can look at the Einstein vacuum equations. And if we assume that we have these constraint equations, which are the equivalent to saying that we have the harmonic gauge condition on the initial surface, then the reduced Einstein-Klein-Gordon system, which was written on the previous slide, admits a global solution on the entire in the entire space, and the metric converges as the time goes to infinity. In a suitable sense, it converges to the solution, the Minkowski metric with psi is equal to 0. And of course, it stays the harmonic gauge condition is preserved. So this is the main theorem that we have. It recovers. So the case psi is equal to 0. It recovers the global stability theorem, the global stability of Minkowski spacetime theorem of Christodoulou and Kleinerman. We do it, however, in this harmonic gauge condition, so it's closer to the theorem of Limblad-Rodiansky. And now we can compare the systems. So if we look at the system, I'm going to talk about some of the ideas that are involved in the proof in the last 20 minutes or so. So I'm going to talk about some of the ideas involved in the proof. And it's a little bit easier to talk about these ideas in the model problem. So what we do in the model problem, what I'm going to do in order to derive the model problem, I'm going to say, so we are looking at this system. Now, if psi were equal to 0, that's a theorem that's known. So this is the Christodoulou-Kleinerman theorem. So I'm going to pretend that we know how to solve that, and because of this, I'm going to take away all the quadratic parts that are already dealt with essentially in the theorem of Christodoulou and Kleinerman. So this means I'm going to take away the term f of the metric and f of the metric and So the quadratic parts of the metric. And now once we take away that term, the metric itself, we can think that the metric has only one component. The metric is not anymore, we can replace the metric basically by a scalar. So I'm going to think that G is a scalar, and it comes into the, so it forces the Klein-Gordon part of the system. And if once we put these things together, we are left with the system that's written there. So we have box U is equal to the quadratic part of the Klein-Gordon part, so that's some sort of V squared, and then a Klein-Gordon operator applied on V, it's U times the second derivative of V. So this is how this model is constructed, and here is the comparison if we keep the terms. So basically, we eliminate the terms that were already dealt with as part of the proof of Limlade-Rondiansky of the global stability of the Minkowski spacetime, and we keep the others, and eventually put all of them together. Now, the model was not derived by us, so the model, I learned about the model in a lecture of Qian Wang. So she derived this model also for the purpose of looking at the same problem. She derived this model, and it was also derived by Le Floch-Ma independently, also for the purpose of looking at this problem. And there's been some significant work on this problem before us. So Le Floch-Ma, they proved global regularity of the system, but in the case of compactly supported and small initial data. So the data of course has to be small, but they also assumed compact support because they use what's called the hyperbolic foliation method. So they need to have control of the initial data on the entire hyperboloid. And they also proved, Le Floch-Ma, they also proved global stability of the full problem, but also in this what's called the restricted case, in which the metric agrees with the Schwarzschild metric outside the ball of radius 1. So this part was done before, and our main this is what's called the case of restricted perturbation, which outside the compact set one assumes that the solution is known, and that because of that, the way that's used is that one gets control of the full solution on the entire hyperboloid, and then one only has to move inside. So the theorem that Benoit and I proved has to do with having a general family of perturbations that are not necessarily compactly supported. And okay, so now, because I want to give some ideas of the proof, I'm going to talk only about the model on which it's easier to see the main issues. So I'm going to state the theorem about the model. So the theorem is the following. If we are, now I can state it precisely because this is simple enough. The norms are simple enough now. So if we are looking at this wave operator and the Klein-Gordon operator in the Fourier space, and we assume that we start with data that's small, and it's small in an energy space, in a Sobolev space, but it's also small when we apply these vector fields x times dx in a suitable way. So we apply it up to 3 times on the metric. So these are the so on the wave component we apply x times dx, and on the Klein-Gordon component we apply just the vector field x. So we assume that the data is small in this sense, and without going to the exact definition, what smallness means that it has decay also at space infinity because we have the weights x times dx. And then the conclusion is that we have a global solution of the initial value problem that I stated earlier, and the solution decays. The solution has uniform bounds that grow slowly in time, and the solution itself decays at a rate that's almost 1 over t rate of decay. So it's almost optimal rate of decay. Now, as part of the proof, the solution, it turns out that it grows in an energy norm. So because the decay it's basically just misses being integrable, the solution will grow in an energy norm. So the way to think is that the solution grows in the energy norm very slowly, but it decays in other norms at a much faster speed. And the norms in which the energy norms in which it grows, they involve Sobolev vector fields, and they also involve the rotation vector fields and the Lorentz vector fields. Now I'm going to describe now this main designer norm that we use. So I'm going to use the mechanism that I said earlier, that we want to describe our solution in terms of energy norms, and we want to describe it in terms of this spatial norm. And in this case, I'm going to describe it. This problem it's quite easy because there are no space-time resonances. So the norms, the Z norm for the solutions, they are very easy to write, and they are written in the following way. So for the wave component, we have two parts. So for the wave components, what we are looking at our function, and we decompose it in both frequency and space. So this projections QJK, what they do is they restrict the function to frequency 2 to the k, and they also restrict it to spatial location of order 2 to the j. And then we take each one of these components. So we think of a function as a superposition of these pieces, and we take each one of these components and we measure it. And the formula is written in the norm for f. So what we do is we put we look at all of these pieces and we put certain coefficients, like of the form 2 to the j, and then powers of 2 to the k, and also the low frequencies and the big frequencies, they have to be separated. And then, so there's the norm. We take the sup, or the sum, over these norms of each dyadic piece. For the Klein-Gordon part, the norm is easier, and the norm is simply obtained by looking at the function in the Fourier space, and it's an L-infinite norm in the Fourier space. It's easier, but there I want to emphasize that there is important. It's tighter in some sense. So for the Klein-Gordon part, one has to do. It turns out that there's no scattering; it's modified scattering, and one has to have this type of norm with the Fourier transform of the function in the Fourier space in L-infinity. Okay, so these are the norms, and now we run the kind of argument that I described earlier. The more precise version of this argument is that we are looking at the solutions, and we measure them in this space H that contains the Sobolev norms and the rotation vector fields and the Lorentz transformations, and in that space we let the solution grow, and then in the Z norm we force it to be bounded. And then this is the same bootstrap that I said, that we assume that up to some time t we control it by some bigger constant, and then we use the equations to show that we control it by a smaller constant. Now to describe this one, I only want to talk about one more significant issue, which is what comes in here. It's the issue of modified scattering. And to explain it, I'm going to ignore the part that has to do with energy estimates. The energy estimates, they can be done, and in some sense they're not sensitive enough to see this issue. So I'm going to talk only about the part that has to do the control of the Z norm. And for this, we have to use the Duhamel formula. And the Duhamel formula can be written in this way. So here I wrote the Duhamel formula for the functions, for the profiles of the function. So we extract the linear evolution, and we look at the profile. And we have these two Duhamel formulas, these two integral formulas that say that, for example, for the wave equation v hat of psi comma t, v hat at the point psi comma t is an integral that involves the integral from 0 to t. So it's the contribution of the nonlinear term between 0 and t to the last slice. There's one specific cascade that we have to address, and I'm only going to talk about this cascade. The main difficulty is there's a certain cascade. If we're looking at the system, we will pretend first that the Klein-Gordon field evolves only linearly. It comes back and hits, so this is the first step. It comes back and hits the wave equation. And hits the wave equation, it turns out that when the nonlinearity of the Klein-Gordon field, so the nonlinearity of the Klein-Gordon field produces something in the wave equation, and that something is of the order of 1 over t. It cannot be better than 1 over t. It's actually bounded from below by 1 over t. And then this component of the wave equation comes back and hits the Klein-Gordon field, and it produces growth, because it comes back and hits the Klein-Gordon field through the second equation, and that would produce logarithmic growth. So we need to, and this is all something about low frequency, so it's not, the energy estimates, they don't play any role here. So we need to deal with this issue, and for this we use a renormalization. It turns out that the profiles that are defined earlier are not good enough. We need to use a logarithmic renormalization of these profiles, and I write here the exact formulas. So the exact formulas are, so we are looking to basically redefine a profile by taking another logarithmic phase, and the phase is constructed in the following way. So the phase at the point ct is the integral from 0 to t of this expression, and this expression is obtained by looking at the wave part of the equation, and we integrate along the characteristic of the Klein-Gordon field. So you're looking at what this contribution that comes u times d to v, and we have to integrate that from 0 to t along the characteristic. The characteristic is given by this t times tc divided by lambda 2 of c. Okay, so now we constructed this nonlinear phase. It turns out that we have to put in this nonlinear phase, and we get the renormalized profiles, which are the correct profiles for the evolution. It turns out that the first one was just the first guess, but one has to look at these renormalized profiles. And then we do lots of bilinear estimates. So then we start from the formula, for example, and I rewrote here the formula. So what we have is the formula. We have an integral from 0 to t, and then an integral over R3. And then we have this phase that comes in the resonance, so e to the is times the phase. And then we look at the contributions of the profiles. So we have to understand this expression. Also, we actually have to plug in the correct renormalized profiles. And then we have this pretty big integral. And then what we do is we have to decompose it correctly in frequency and space. And depending on the size, one can integrate by parts in time in some ranges, and one can integrate by parts in space in some other ranges. And at the end of it, we can control all the terms. So the proof, I'm not going to go through the details of the proof because it gets quite technical. It turns out that the proof is a little long. So these proofs, they turn out to be more, this is about 100-page long. There's no, in some sense, there's no quick way around it because just the proof of the stability of the Minkowski space, and there's not short, and we have to do that anyway. So we have to cover the case size equal to 0 anyway. So there's no real way around that. There's no proof of these things like under 30 pages or something like that, because one has to look at this kind of expressions. They are long and there are many cases to consider. In some sense, once you have the good norms, it's kind of like downhill from there, because proving every case at a time is not hard, but constructing the norms takes some effort, because one starts with some kind of inputs, and then it turns out that some are not quite right, and then one has to plug in those inputs and figure out what one gets at the second level. And the stationary points of these expressions, they keep coming in because they are the ones that produce, it's the stationary points of these phases that produce basically the outputs at any time. And one has to count exactly how much they are. And one other thing that's important here, which is called space-time resonance, is one has to integrate by parts not only in space, but also in the frequency eta. And in order to integrate by parts in the frequency eta, one needs to know that the profiles are smooth enough in eta, because you want to say the profiles are smooth and the phase is the one that oscillates. And the way to do that is to use, the only way to get smoothness in eta is to use weights in the physical space. So this is how the weights in the physical space are motivated, because one has to look at this expression and keep integrating by parts both in the spatial variables eta and in the time variable s. Okay, but eventually, so eventually, once we do the renormalization, we can close the argument, so we can prove these estimates and close the argument. Now, as I said, it's a long proof. However, there is one critical enemy in all of this, in any of these proofs, that one has to think about. There are lots of smaller enemies that's part of the proof. There is one critical enemy, which is if you have solutions that are stationary in time. If you imagine if you have a solution that doesn't decay in time, then that would be the proof, because what we prove is, our proof says that any solution that starts out as a small perturbation of what we want is going to evolve and decrease and eventually converge to the solution that we want. But imagine that's not true. Imagine that you have a bunch of solutions that are stationary solutions, which would go closer and closer to the original the solution that we want to prove is stable, and those would be the proof. The proof would not be able to work if there were such solutions. And it turns out that for the Einstein-Klein-Gordon system, there are such solutions. There are these small solutions. They're called the mini bosons. This is something very special. So in most problems, there are no such solutions. For example, for the Einstein vacuum equations, there are no small solutions of the Einstein vacuum equations. Or for the waterways, there are no small waterways. But for the Einstein-Klein-Gordon system, there are such solutions that were discovered numerically a long time ago, but they were formalized by Bison. We read about them in this paper of Bison and Wasserman. They are standing wave solutions of the Einstein-Klein-Gordon system of the following type. The metric is the metric that doesn't depend on time, and it's a radially symmetric metric. So it's a metric that's spherically symmetric, and it has only two components that are non-trivial. They're both functions of R, and the two components are delta and A. So this is the metric, and the Klein-Gordon field is it's of the form e to the I omega t phi of R. So this is a standing wave because it's not exactly stationary because of this factor e to the I omega t. So the standing wave means that the Klein-Gordon field keeps moving up and down depending on t. But solutions like this, this would be inconsistent with the theorem. So if we cannot find a way to block this kind of solutions away, then they would be inconsistent with the theorem because they don't decay. So these solutions, they don't decay. And it turns out that, so this is the analysis of Bison and Wasserman. It turns out that these solutions, they can be made small. In many ways, they can be made small. You can think, for example, I didn't want to get into too many details here because they're pretty complicated. So we have basically three functions we have to look at. So we have the functions delta, A, and phi, and they satisfy a coupled system of ODEs because they're all functions of R, so they only depend on one variable. There's a coupled system of ODEs. One can think morally that the function psi of R would be something like A times e to the minus A R. So psi of x e to the minus. So one can think it could be something of this type. It's more complicated because it also has oscillatory components, and it's more complicated in many ways. And one can think that there is a sequence A goes to 0 for which there's a sequence of number A for which one gets solutions of this type. Now, if you look at these kind of solutions, these are very small in many norms. Like, for example, these are very small in L infinity. They also decay exponentially fast. But they're not small in the kind of norms that we use. So what do we do? Like, for example, this would not be small in L2 because you'd have, when x is about 1 over A, then this would be of size 1, and then there is a coefficient A in front, but it doesn't beat out the contribution of the L2 norm. So what we're able to do is to, so it turns out that there are solutions of this type, and they don't affect our problem because even though they are small in many norms, they're not small in the norm that we use, and we use a strong enough norm in order to block these kind of solutions out. And it's quite remarkable that we can do it this way because it's, in many problems, if there are these small solitons, of course, at time t is equal to 0, you can say that you use a strong enough norm to block them out, but then they tend to come back. So you could have some kind of soliton forming out of data, or at least not control the topology, not control the norm strong enough at later times in order to still block out these solitons. In this case, it turns out that we were able to do it, and so these mini bosons, they don't play a role in the proof. Okay, so eventually we close this argument, and so we run this argument, and we prove global stability. Okay, so I'm going to stop here. Thank you.